Alright, so this is the video for the controls project for ET468. It is for the final project submission right here. The first thing I did was kind of had to think about what I wanted to do, and my initial idea was to do something along the lines of um, like a chemical process for I don't know, different chemicals that manufacturers would use, or maybe chemicals for like medicines or something like that. But I figured we've already done one that's kind of like chemical related with the water system, so I wanted to get away from that a little bit. And I decided to do something that was more common for everybody, and that was a cruise control system for a car. And I'm pretty sure that like all vehicles made nowadays um, have cruise control systems installed on them, so they should be a pretty common thing for everybody. The tools I used was LabVIEW, seen here. I also used MATLAB just a little bit to make sure that some of my transfer functions actually made sense, and to just kind of make sure that the curves weren't um, really wild or out of control, and that they all had some kind of steady state. I also used a little bit of YouTube to try to figure out like how to make a system from scratch, since reading through both of our books was kind of, they always talked about like they gave problems that already had the transfer function or already knew like mass or potential energy and stuff like that, and so trying to find it with no information was actually, in my opinion, about the hardest part of this project. So that brings me to the first part, which was the initial challenge, and that was to find the actual values to use for the transfer function. And kind of following along with the book and like the mechanical parts that we used and everything, I found the mass of the car, and what I decided to use for an example was a Tesla Model S. And so I decided to use a Tesla because at first I was just going to use a standard like Toyota or Honda or something, but I didn't really want to mess with the whole idea of like having to figure out how much horsepower the engine made, and having a horsepower graph and going through the transmission, and trying to figure out how the torque changed for everything, just because I kind of felt like I didn't have enough time to be able to get all of that done and still have a system that worked at the end. So I went with the Tesla, since it's a direct drive um, AC motor system. And so the specs I got for that, roughly the weight is about 2,107 kilograms. The motor torque, it's kind of hard to find exact numbers because um, torque and horsepower given by Tesla don't always match tests that were ran. And so what I did was I tried to find motors that were freely available to use that were as close to the motors that Tesla uses. And in those, the motor torque ratings were about 1,373 Newton meters. And I figured that this was probably the average pull-up torque, and it didn't really consider like the breakdown torque, since um, I doubt that the motors in these cars are used to operate in the breakdown area, just because of like the slack and everything. Um, okay, so the first thing that I would want to do, and I'm just going to kind of walk you through what I did here, is open up MATLAB and go ahead and I'll show you the transfer function that I ended up using. And so I want to make my S variables there for the start. My transfer function is going to be, it's actually really, really big, surprisingly. And, or maybe not surprisingly, because all the examples we worked with, everything was always just a few kilograms. And so having this car at 2,100 kilograms is led to some gigantic numbers. And I tried to pull it down into a second order circuit by a second order function, but I couldn't get anything that would stay stable. And so, oops, mess that one up a little bit. So, what I ended up doing was just using the stock numbers for it, the weight and the torque, and then I found that torque on the top was about the best number that I could use. I could scale it down a little bit, and I could also get this into a second order formula, but like I said, instead of having something that oscillated a little bit and came to a steady state, anything that I tried making um, was way underdamped, and it would just continuously get bigger and bigger. And there was really, I don't know, I spent at least probably a solid 2 days just trying to figure out the math on it. And I think my biggest issue with that was I couldn't find any kind of dampening force. And that's just because I don't know exactly what would dampen the car accelerating other than like air drag and maybe if it's on a hill, some kind of incline or something along those lines, and then just like whatever isn't already affected by the weight of the vehicle. So I just kind of left that alone, left it as first order, and decided that I would model it based on that. And just like from some of the videos that I watched, there were other people that did something along that lines too, just because um, anything else wouldn't give, you know, good results, just like I wasn't getting good results. And so you can see here, this is the step response graph from the transfer function, and it gives a little bit of, you can see like here we hit 90% in 3.5 seconds. We're roughly stable in about 6 seconds, and then we actually get to peak at probably about, it's more than 14. Oh, it's not going to say here, but maybe it'll say right here. Probably at about 15 or 16 seconds. So greater than 14. Okay. So this is included in my report right here. Another thing that I wanted to do just to make sure that there weren't any numbers that were getting thrown out that were too big was just check the info also, just to make sure that everything seemed, okay, you can see here, peak time 16.1 seconds, just to make sure that there wasn't anything wild. And like I said, it's a first order circuit, so you shouldn't expect any really oscillation or anything, and there's nothing, damping it, so it's not going to be over or under damped or anything like that. The next step from here, once I figured that, all these numbers were fine and everything, was to come into LabVIEW and just start building. And basically, my first run of this, I wish I would have saved it separately from, I just kept overwriting and saving, was I made my own PID controls kind of related to what we did in class. And it wasn't really, what did I do? Working out the way that I wanted it to. And so okay, didn't mean to click on that. And so what I ended up doing was going through a couple different PID controllers from the functions palette, and I ended up going with like the most standard one I could, and that's only because some of the other controllers, they are really hard to follow, and a few of them that I started working with, I realized that they were hardware limited, so you actually had to have some sort of hardware input. And so I ended up going with this one, and it gives you a choice between 3 different instances to use. You can use academic, parallel, or series. I tried all 3 of them. The best curve I could get was with academic, and so this gives you your um, your multiplier here for your proportional gain, but for your derivative and your integral, you actually get your time constant to use instead. And if you go to like parallel, you can see you get your amplifiers instead of your time constants for those, and then here you do get time constants. But this one actually was probably about the worst one in my opinion out of the 3. So I stuck with academic and decided that I was also going to use the time frequency multiplier at first, because whenever I did have the second order circuit, I had a time frequency of about 450 seconds. And I ended up not using it, and I'm just leaving it to its default of 1. But I had it so big that I actually couldn't really, almost no changes that was going on here were making any difference because of just how large this actually was. And I would think that would make some sort of difference, but really they didn't. This was your constant for your proportional gain was about the only one that was actually, making any sort of difference. So I stuck with that, and you can see I left the controller for the time frequency in also, but I ended up not using it. I used the standard transfer function instead of just using like a numerator and denominator setting. And then I summed that with a starting speed, and because you wouldn't use a cruise control starting from 0 miles per hour. You would be going, maybe 20 or 25, and you would want to speed up to 30. And so you would use it for something like that. Or if you're already at 30, you would want to hold it at 30. And in this example, and the examples that I ran for the report, I had it simulated cruising at 20 miles per hour and then instantly setting it for 30 miles per hour. So I'll show how that looks, and then I'll show also stepping from 20 up to 30. So 10 increments of 1 mile per hour each, and kind of show you how it responds in a step fashion instead of just the initial 10 mile per hour input. Two other inputs you can see here are your hill incline and your headwind speed. And I use these just to kind of give something that would affect, like have more of a real life effect. And just because you're almost not going to travel flat anywhere, and there's always going to be times where you encounter hills either up or down. And so I added those and then went through and did this little formula here for converting speed into momentum, and then finding the force of the slope and the force of the wind, and basically taking the momentum math, which comes from this gives you momentum math, which comes from car moment minus F slope minus F wind, which is the opposing forces acting on each other. And then I just converted momentum out by getting rid of the weight of the car again. And that is shown here. So that actually comes out to be total momentum. And then what I also have is car momentum, which is something that you can see in the front panel here. This is going to be how much momentum the car wants to have, and this is how much it actually has. So this number, if you're going up a hill or you're facing a very, very strong headwind, this number is going to be smaller than this number. But if you're actually going down a hill, then your total momentum is going to be greater than your car momentum. And that's only because the car actually wants to go slower than it is, but because you're going down a hill, it's going to be speeding up. The only time it's not, and there's a small little, I've got rolling friction included, so there's a small little, I don't remember, it's very tiny, something like that, like 2 micro, I don't know what this would be, micro degrees, I guess, that makes up for the rolling resistance. So if it's something like that, then the car will roll without slowing down or speeding up. But like we know, that's in a perfect case scenario, and that actually isn't something that's going to happen. So I had the array builder here to show the speed versus the cruise control speed versus the total momentum. And total momentum I leave out of the graph because it always spikes up way higher than the speed. And that's just because momentum is not the same as miles per hour. So it's going to be quite a bit higher because of that. Other things I included was a digital speed indicator. The speed gauge, which you can see here, I included the slope of the force of the slope and the force of the wind. And that's just so once we start the project, you'll actually see, how much force the slope or the wind is putting on the car. And so it's basically, you'll just look at this number right here, and then you'll subtract or add these two numbers, and that'll give you this number right here. So to kind of explain the numbers and how I got to them real quick. So the 2107 is the mass of the car in kilograms. 9.8, like we know, that's the acceleration of gravity. And then the sine of the hill divided by 100. So if you're looking at, like, hill slopes are given in degrees, and they're also a percentage of degrees. So um, this is the formula of it acting on it. So if we had like a 90-degree hill, you basically, you'd be driving straight up, and you would see that this would make the car basically almost drop at the speed of gravity in reverse. And so about the biggest that I used on this, though, was about 10 degrees. Force of wind is 0.246, and this is the mass density of air. And so I guess basically the way I can kind of relate it is it's also like saying like the viscosity of air, and it's really, really low. And that's just because, like, technically air, or like the air and liquids and things, are all the same. And just because there's water moisture in it. The 0.5 is a constant, the 1.2 is a constant. Wind times 1000 is just doing a conversion there, and then we divide by the mass again. And 2.34 is the frontal surface area of a Tesla Model S, and this is in meters squared. And so I was going to also include the slipstream effect of the vehicle. And through a little reading online, doing a little research, I found out that the Tesla Model S is the most streamlined production car ever made. The number on it was so minuscule, I don't remember off the top of my head now, but the car has to be going, I don't remember how fast it is. It was over 100 miles per hour before there is a noticeable drag on the motors. And so I just didn't even include it because that was a lot more math, and which mean that the simulation itself was going to take more time. So I just left it out because in reality, on the graph that it's going to show, you wouldn't even see a difference anyways. So the goal of this system, after I made it and ran it a few times, I went online and got to reading, and found a study that somebody did with what's comfortable accelerations for humans. And what they did was basically went on a subway somewhere, and they recorded the acceleration of the subway, and they went faster and slower. And they did this as a test to kind of see, like, they asked the passengers how comfortable or discomfortable they felt, and then they also observed the people to see how much, like, they swayed during takeoff, and if they had any bags or anything with them, if the bag slid, then they recorded that and everything. And they had accelerometers on the subway to tell just how fast the acceleration was going. And in the paper that I wrote, I've actually got the link to it and the citation and everything. And so if you want to go on there and read on that, you can. So what I did basically was I set goals for myself. I didn't want this to shoot up as high and as fast as possible, just because if it had a near vertical takeoff from 20 to 30, then that would give you whiplash, and it wouldn't be realistic, because you can't accelerate faster than gravity's pulling you down, or your tires start spinning out, and you don't have grip. And so just to get away from saying, like, if the car has grip or not, I kind of also added these to it. And so my first goal was to create an acceleration curve that had less than 5% overshoot. And so in that case, if we say that we're going from 20 to 30, and I'm using 30 as my 5% point, so I don't want anything to go over 1.5 miles per hour. So the maximum my car can see is 31.5. And I think that's pretty realistic because I know on some cars, if you put 30, it'll come to 30 perfectly and stop. And there's other vehicles where it'll speed up just a little past 30 and then settle back down a little bit, especially if you're going down or up a hill at a time. Or if you're on, like, say, highway speeds and you're doing like 80 or 90 and you're real close to a vehicle in front of you, sometimes you'll speed up just a little bit too quick just because there's the slipstream effect from that vehicle. Um, so the second one was maintain less than 1 meter per second squared of acceleration. And this is well below the limits of gravity because, like I said, we would have to get to 9.8 meters per second squared to exceed that, and that's when the tires would actually start losing grip on the road. So I just kind of wanted to avoid that a little bit. So to set it up, I used all sorts of different speeds, but the first thing I want to do is make sure that I have my time set for 15 seconds, and I added this so I could run it up to different time settings without having to constantly come back in here and go through all this to figure out, how fast I wanted to set everything. And actually, while I have this open, I'll go ahead and talk about it too. To get this to slow down and be as close to 1-to-1 with real world time as I could, normally this is unchecked. And so what I wanted to do is bring it into the timing source and then pull up a 1 kilohertz clock. And you would think that the math would work on this, but unfortunately it's off by just a little bit. So what you have to do, if you want 1 second of recording in here to equal 1 second of recording in real time, the period's set to 66. And I don't know if this is like computer specific. Maybe faster computers you can have a lower number or a higher number. I don't know. But 66 was what I found to be. It's actually just a little over 66, but the choice is between 66 and 67, so I picked that one because it was a little bit closer. And then I left my step size at 0.1 just so I could get 10 samples per second, only because I figured this was adequate. It's not terrible, but it definitely it's something that my laptop can handle without freezing up. So this is basically what I left it at. So what I was saying, to avoid having to come in here and change this every time, what I did was just went ahead and made this control, and then you can control it in here to set this for whatever time you want it to be. The high frequency, from the wave, like I said, I just left that at 1. My cruise control speed, so like I was saying in my sample, I ran it to 30 miles per hour. My starting speed, I want to start at 20. And then, like all things, the initial sample, 100. When you run it, you'll see there's really no movement down here at all. It's going to stay at 20, and even if you bring it up to 10, see there, now we're at 10, we're going to see it, I have a couple bumps up, but if you compare it to the last graph, you can see there it basically stopped. And so right here, we're stuck at 20.07 miles per hour, and it's really not going to change too much from that. So I'm not going to go through and spend 20 minutes showing you how I went through and mess with this. And I was wanting to do the Ziegler-Nichols way to find these numbers, but unfortunately it just wasn't working out. And like I said, that's because I was having kind of a rough time getting graphs that made sense, that were outside of first order. And so basically, from what I understand with them, like, you either have to have a second order and convert it down to a first, or you have to have a good second order to be able to use that. And so basically what I did was just a lot of fine tuning and taking values and doubling them until I saw something that I kind of liked, and then doubling them again until I found something I kind of liked. And then I started in with the integral time frequency and decided that messing with just these two right here, so messing with KC and TI, you can, don't worry about the KI or the KP in this one. I put those so that it was noticeable for no matter which of the 3 different types of controllers that I wanted to use. So what I ended up finding was getting a time interval for this one to be, 0.95. And then this, I left it 75. When ran, here you go, just shy of 31.5. There's a little bounce back here, but it was within the range that I want right here, and so you can basically say right about here, we are at our final speed. We have less than the 5% overshoot because we're at about 31.2, 31.3, something like that. 31.5 is what I set my goal as. And then whenever I came through and did the math, so I found the most linear portion through here, and by exporting this into Excel, and I found that the resulting acceleration was 0.82 meters per second squared. And then in terms of how many G's it pulled, it was 0.083. So it wasn't even 1/10 of the amount of gravity. And so, like I said, this was only the PI controls. And just from being in class and then reading a lot of sources and everything, for the most part, a lot of systems don't use any kind of derivative, so they leave this at 0. And it works for this, but I figured that I kind of wanted to give it a try, and I had seen some other sources talking about if you have a high power, high speed system, that sometimes it's worth giving the derivative time interval or amplifier. Like it's worth at least giving it a try, because sometimes you can get this curve to look a little bit better. And I did that, and I ended up coming up with numbers that I thought looked better. And this is what I ended up getting for a full PID control. And so you can see the peak is actually just a little bit less in this one. And it takes longer once it dips back below. It takes longer to come up, but it gets to, within the plus or minus 3%, just a little bit quicker. The only draw of this is that you have the initial jerk, but the overall acceleration is actually just a little bit less too. And so in the previous one we had 0.82 meters per second squared. This one we actually have 0.79, so it's 30 millimeters per second squared less of acceleration, which I don't think that would really be too noticeable by anybody, but it's noticeable by the computer, so I'm going to consider it a little bit better. And where the last one pulled 0.083 Gs, this one only pulls 0.081. And so it's not as rough on the body, it's got a little less overshoot. And like I said, the only drawback is it stays below 30 for just a little bit longer. And just to give kind of an idea of how the slope for the car works, let me go ahead and turn this up, and you can see I'm making the incline go up, and you can see how it's affecting the graph. So I started it right about right here, and then you can see, like, okay, we're going back down a hill, and so it rose up to just a little over 30.5 miles per hour, and then it came back down and settled down. And that was the kind of idea of this. The idea was initially that you could just put in a number, say like, I don't know, 25, and it would go from 0 to 25. The only hard part was I was having a hard time trying to find a function or a formula that I could run in here, or something out of the functions palette that I could drop in here to compare the time ran to the slope. And I don't know, I need more training in LabVIEW or something. There was something that I couldn't quite get to work, and any external timing calls that I wanted to made within the program here were just giving too many errors that I couldn't fix. So I ended up just overall leaving it alone. But the idea was that you could start and have it set at like 25, but you see if I come to 0, it shoots up. So there's no gradual 25 to 0 or 0 to 25. So now we're back at steady state, and if I hit 25, it's an instant drop instead of being a gradual drop. So that's one little issue with it. But if you just take and hold the mouse down, or just click really fast, you can see how it actually makes a difference in the system here. So just to run it one more time, let's say we're at 0, 0, actually, let's make it -10. Say that we're going down a hill whenever we hit it. So we're going to see we're actually going to shoot up just a little bit quicker here. And, but, I mean, it caught it. And we're going down the hill, and then we're going to come up a hill. So you can see how it's actually fighting to not get at 30, but the system's holding its best. So it's at, I don't know, about 29.8, 29.9. And it's just basically going to sit there and try to keep that same speed over and over. I'll go back to the PI controller to show you, so you can kind of see how the wave shape differs between the two here. Let's see, set that to 0. We'll set this back to 0 also. Oh, also I didn't point it out, but you can actually see the amount of force that the slope is putting on the car. And like I said before, the car momentum, this is what the car wants to have. This is what it actually has. So if you take this minus this, you're going to get this. And if we leave it at 0, whenever we start it, you'll see that these two are actually going to be the same. So if I pause it here, we'll go through this. So if I pause it, you can see that they're going to be the same. But if we go in, and now we came up, we're settling back down, and then we start driving up a hill, you'll see that it's going to slowly work its way back up, and just like the full PID control, it's going to sit here and oscillate, but you notice it's just a little bit lower, and that's because it doesn't have that derivative controller looking out to the future trying to predict what's going to happen. And so it basically, every time it goes through an iteration, it sees the incline for the first time again, and it's just judging off the past because of the integral control. So that's pretty much it for that. I don't think there's anything else I need to talk about here. The headwind, I could put something in like this, but because the car is so aerodynamic, it is oops, left that at 58. It's gonna spike and come back down. Because it's so aerodynamic, you'll see that it doesn't produce hardly any force by the wind on the frontal area right there, and that's also because the frontal area is aerodynamic and has that really small frontal area. So this is only almost negligible, but I added it and did all the math before I realized how much it doesn't really matter. So I just left it in there. But yeah, that's it. Thanks for watching.